So we now want to define the center of parallel forces. Let's first see what parallel forces are, and then we can see what the center of parallel forces means. Okay, so let's take up a rigid body. This is frame F, this is point O in this. Consider a point R, and this has Fr equal to Fr in direction E. Okay, this is point 1, this has similarly F1 E, this is N, this is Fn E. Okay, and say this is I, this has Fi E, and similarly you can have F2E and so on. Okay, now you have this parallel force system consisting of forces Fi E hat acting at Ri. Ri is the position of the ith point. Okay, just like R is the position of this point R. Okay, so I can go from 1 to n. Okay, so this n is the last point on this, and f of r is not equal to 0. So Fr is the resultant. Okay, just for your information, Fr is the resultant. Now this Fr passes through a point R called the center of parallel forces. This is irrespective of direction of E. Okay, so whatever be the direction of E, it will still be called the center of parallel force. So let's find out its magnitude. We already know that Fr is the resultant, so it will have Fi summed over all i's and E, since all the F1, F2, F3, Fn's are in the E direction. Similarly, the moment about O will be summed over I again, Ri cross Fi, or Fi we can write it as Fi E hat. This can be written as Rr cross Fr. Okay, the reason is this particular term can be written as Fr. Okay, and this is equal to, can you tell why is this equal? Why is this equality holding? Hold on, this particular thing. think about this one. Okay, why? This would be equal to RR cross, this has to be brought in, summation Fi E hat. Then let's call this as equation 1. Now this implies that this is summed over I Fi or R minus Ri Fi cross E is equal to 0 for all E. Okay, so what you have done is you have subtracted this from this. Okay, and then you would get a 0. So once this is known to be, this cross product is known to be equal to 0 for all i's, the only implication is that this square bracket is 0. That would mean that RR is sigma R I F I I'm sorry, there's this term. Okay, this had to be there because when you were trying to subtract a scalar from a vector, which wouldn't have been possible, so there had to be a vector sign somewhere. Okay, so RR is equal to RIFI, and this can be divided by, or should be divided by, Fi summation over I for all E. This is equation 2.19. Okay, so this why you can answer just by understanding enough what a resultant force Fr is. Okay, it should essentially create the same effect, and that's why that is there. Okay, let me just now remove this. So get a more concrete answer, please. Okay, so now that you have the magnitude of Fr, you also know where Fr acts because you know the position vector of this R point, that's the center of parallel forces. So one of the statements which I'll write in red, and that's for you to sort of interpret, is that for specific direction E, say equal to E1, okay, E equal to E1, equation 1 yields the equation of a line parallel to E1 which passes through R. Therefore, equation 219 yields the common point intersection R of various lines obtained by changing the direction of E. Okay, so this is something which you should be able to write. Okay, I will tell what you have to do. Write equation 1 and replace E by E1. Okay, that would be like one specific E1. Then write equation 1 again by replacing E with E2. Then write equation 1 again by replacing E with E3. So now you have the equation of 3 lines. Okay, and then equation 2.19 is true for all E's, meaning E1, E2 and E3, and hence it must be a point which satisfies all the 3 equations of the line, and therefore this statement in red. So please do this exercise and do not move ahead without actually convincing yourself that these will yield equations of a line which will be parallel to E1. Okay, passing through R. Okay, just check why are they passing through R. So if there is also a doubt, you please write the vectors in terms of scalars. For example, this will be rx I hat plus rry j hat. Okay, so this is a point, and you should perhaps y equal to mx plus c or ax plus by plus c equal to 0, whichever forms of line you seem is okay, you should go ahead with that. Okay, so this is the x coordinate of R, this is the y coordinate of R. So please do this exercise and only then you should move ahead. Okay, so this was for obviously discrete points, and it's not very hard to extend this concept to a distributed force. So let's say you have this small mass dm. Okay, this point is P, this is O. Okay, and then you have this point over here, let's call it G or C. Okay, not R. Now this particular point will have df acting over here, rp. Okay, this would be clearly rg. So let's see what it means. For a distributed force, clearly this summation in 2.19 will be replaced by integration. So for distributed force, in 2.19, replace the summation in 2.19 by integration. So you know this particular drill. Okay, and the center of these parallel forces are actually called the center of gravity. Okay, and that coincides with C, which is the center of mass. So let's see, Rg is equal to Rr, just like in the previous case. Now the summations have to be replaced by integrals. So how would that be? Rp into df. Okay, and this is summed over the entire mass. And what is the force? GDM. Okay, because that's this, sorry, df. Okay, now df is equal to g dm. The small force of gravity on this mass dm is actually dm into g. Okay, so that's where you have rp into g dm and g dm. This is m, this is m. This g gets cancelled since it's a non-zero quantity. So you can recognize this statement. This is actually the center of mass. Okay. So in this diagram, the center of distributed, okay, not discrete, distributed parallel forces is uniform gravitation, df equal to g dm on mass. So g is also called the center of gravity. C is center of mass. In this case, both of them will coincide. Okay, so this was about point, and you know that we keep on extending our analysis to both line loading, then aerial loading, and so on. Okay, so let's see how that works out. Let me first draw the diagram and then I'll explain what it is. Okay. Trying to look for a different color. Okay. Plane curve C1 and say, okay, so let's try to understand this. So consider a parallel force distribution Fl in the direction n units will be Nm, Newton per meter. This is normal to the plane curve C1. Okay, so C1 is the curve which is, you can see in this diagram, it's in black color, and it has a loading, distributed parallel loading FL. Okay, now if you take a small part of it, okay, let's first define how this is acting. Take the small part ds later on. So it's C1 at every point of curve erect an ordinate parallel to n, okay, and this will be equal to FL. So take any point, say this point Q, okay, this point, and you have this small length associated with this element. This is ds along this curve. Okay, now you can take up this strip over it. Similarly, you can create for this area a strip which is parallel to n, okay, and so on. So for the entire curve, for the entire curve you can do the same. And what will this result? This will generate the loading surface. Okay, so a small part of this, for example, will, the force on this part ds is equal to FL ds, okay, and that will be equal to dA. We'll come to this later on, but as of now you can see this loading surface. So this loading surface is made up of lots of strips like this. Okay, so just to repeat again, this surface is just representing the loading. It's not a real surface as such, in the sense you can't keep anything on this surface. Okay, so loading surface, it is shown. Now the resultant of the simplest resultant, sorry, equals the algebraic area A of the loading surface through its centroid C star. So let me show this statement, what I have written in black. The simplest resultant equals the algebraic area A of the loading surface if A is not equal. So A is the area of the loading surface. So let me just show that. A is the area of the loading surface. Let me put that over here. Area A. So df is the force on the small element ds, that is equal to FL ds, okay, and this will be equal to dA. This dA is essentially this area, the area of this strip, okay. Now the resultant force is f into df integrated over the whole. Okay, since the direction is the same for all these strips which you draw, okay, the direction of this forces will always be parallel to n. Okay, that's why for all of them it will be like this. Now you can convert this into area, dA into n. Since df is equal to dA, so you can replace that over here, and this can be written as a into n hat. This is equation 1. Sorry. So the total resultant force is equal to a n hat. Now the next point is to find its position. Let's do it first of all in terms of the centroid. So the statement says that the simplest resultant equals the algebraic area of the loading surface. Okay, that part we have shown, and it acts through its centroid. So we have to write the position of R, okay, in terms of the centroid. So this is the R, okay, and the resultant is acting over here. We have to find this position R, okay. So let me first define write the centroid. Sorry, RC star. This is RP TA A, okay. So this is something which we already know, that any point, and this centroid again is not of the line, okay, this is of the area, also so called. Okay, so this is of this P point, if you see, is somewhere over here on the loading surface. So RC, so this is the centroid of loading surface. Okay, so this is the definition of a centroid. We knew that already. Now we want to write it in terms of let's say RQ plus 0.5 FL n hat df. By f. Okay, so this point is Q in the center. If we take an area, then we take the point inside it. If we take a volume, we take the point inside it. So this point Q is inside it. Sorry if I had mentioned that it's at the end. Okay, now RP and RQ is there. Now can you see why this distance this is equal to this? Okay, so you have to just write a vector RP in terms of RQ, and then you have to go up on this. Okay, going up on this in the direction n, that is 0.5 into FL into df. Okay, if you were going all the way to the top, then this 0.5 would become 1. So P is, if you see over here, is the centroid of this particular strip. Okay, this strip which is marked in blue over here. Okay, so this is something which you should write. Okay, explain exactly, draw a nice triangle and do this. Don't just leave it by listening to what I have said. The only way is to do it yourself. Okay, that means that RC star is equal to RQ df to f plus something. Okay, that something you already know what it is, in the direction of n. Okay, now this RQ df by f is actually equal to RR. If you have a doubt, sorry, you should see over here. Okay, this thing. So RQ df, okay, over here we are calling it the point, and this is Q is a point on the line clearly. Okay, P is the point on the loading surface, Q is the point on the line. So RR is equal to RQ df by f integral. Okay, and this is again n hat. So this statement now can be said that Fr acts through its centroid. This implies Rr is equal to Rc star minus something in the direction of n hat. Can you see n hat? Okay. Now this means that Fr acts through the centroid, meaning if I had to mark a point on this Fr, that would be, the centroid would be somewhere over here, C star. Okay, so that way we would say that it passes through the centroid. Okay, since it's also in the direction n. Okay, now this loading which we have taken, this FL, can have two examples, two simple examples. One is like this. So you have Q naught Newton per meter. Okay, and clearly it will pass through the centroid C star. So the resultant Fr will pass through this. That value will be equal to AQ naught, and this is A by 2, this is A by 2. Okay, so this is something which we have just seen, and if you have this sort of a distribution, okay, the resultant of this, so this would be what, maximum value is Q naught Newton per meter. Okay, and the loading is actually increasing with the length. So this is very easily seeable. Say if you have a container of water, okay, and the loading over here will be the maximum because the pressure on this particular face will be maximum, or in this particular line will be maximum, and as you go up it will keep on decreasing. Okay, so this is a similar sort of a behavior, a triangular load so called. So the resultant of this will also fall on the centroid, and as you may be knowing that the centroid of a triangle like this is actually 1/3 up from the base. So if this entire length is A, this is a by 3, okay, and this is 2a by 3. Fr will pass through over here, and what will be the value of Fr? This will be the area under this curve, that is half into q naught into a. So these are the two simple distributions of line loadings on a line, and how to find the resultant of parallel forces in this case. Okay, over here you can see that these will be parallel forces, all of them. Okay, now let's take up the next case of area, obviously. Okay, so clearly I'm in this particular case, line Fr will be equal to Fl s into n hat, acting through centroid. So these results are also valid on a spatial or a plane curve. With force density. Okay, Fl or Fs can be called as force density. Fl in the described as force per unit length projected along per unit length projected off the curve in a plane normal to n, to n. Okay, so let me show that. The idea is that if you have so over here this line was lying on this particular curve C1. It was a plane curve. Okay, if you have a spatial curve, in the sense it's not lying across a particular plane, then you have to take the projected curve. So let me just draw that. Say if this is a spatial curve, now I am drawing it like this so that you know that this is a spatial curve, and this curve is clearly not on any plane. It's a 3D curve. Okay, and you have obviously a loading like this. Say this is Fl. Okay, and then if you take up a small ds curve, and this is the stripe with which you are there, and then this area is equal to FLDS1. Sorry, I should not write this. This curve is ds. Now what I do, I project this curve on this plane. Okay, then I will say perhaps have something like this. This is the projected curve. Okay, and this is ds1. This point in the middle is clearly q. Okay, so this will now be dA1 equal to FL ds1. So you clearly know what is the difference between A and A1. Okay, if not, I'll show it to you in the next figure. So in the next one, I will just draw the projected curve. Okay, I will just draw this part. Okay, so if this part is ds1, okay, let's consider this one. So I'm calling this as E and F, so that you know that I'm only drawing the projected. So in this case, you have to just calculate this area. That will be dA1 equal to F L ds1. Okay, and the center of this will be centroid of this curve is over here. So this is the centroid of this area. Okay, R acts somewhere like this. The resultant FR would be AN, just like in the previous case. Okay, so this is why we say that the results are also valid on a spatial or a plane curve with force density FL n hat, force density described as force per length projected of the curve in a plane normal to n. So you have to project this on a plane normal to n, and you can use similar formulas over there. Okay, fine. Okay, let me not write this over here. Okay, I think this is more correct to write it over here, the projected ones. Okay, now the next stage is obviously the area, because we have already done the volume, we have already done discrete points, we have already done a line, both planar and spatial. Okay, so next is the distributed force. Fs n hat normal to a plane area A. Okay, now you have to do a similar thing which you had done for the line one. Okay, at every point of contact, at every point of contact of the area, erect an ordinate parallel to n equal to Fs. Okay, and then the solid so generated is called pressure surface. Just like it was called the loading surface over there, now it will be called a pressure surface. So let's see. Okay, so if this is the, let's call this as n. Sorry, this be the origin, okay, and this be the n. And this is, so this is the surface which you have already shown in black. Okay, now if I take a small area dA over here, okay, and I will now have to create an ordinate which is parallel to n. Okay, so I do it like this, let's call it something like this. Okay, and P is the center of this small sort of this ordinate which I have drawn for this area dA. Clearly this point is Q, the center of it. Now if you keep on doing this for every other small area which is in contact, you will get a surface which will actually look something like this. Okay, not actually a surface, it will be a volume generated. Okay, I hope you get the idea. You keep on doing this for all the small areas, and this is called the pressure surface. Okay, the surface is this particular part of it. So this is V. Okay. Now the simplest resultant equals to the algebraic volume V of the pressure surface if V is not equal to 0 and acts through the centroid. This is something we will show. Okay, you shouldn't see me as a person who writes first and shows later. Unfortunately, that's how it's in the book, and because we are reading the book and you are also following this, so that's the order, but we will show this right now. Okay, so dF is the small area, small force on this area dA. That would be clearly Fs multiplied by dA. Okay, and Fs multiplied by dA will be a small volume of this volume which you have generated. So V is the total volume. Okay, dV is the small volume of this solid which you have generated. Now Fr, which is the resultant force, is dF into n. Okay, all the forces will be in the direction of n, no matter what area you take, all the dFs will be in the direction of n. And this is converted to dV into n hat, and this is Vn. Okay, so this is the algebraic volume V of the pressure surface. So that part is sorted. And where does it act? We have to show that it again acts through the centroid of this volume, this solid which is generated. So we'll proceed similarly. We will write the centroid of this. This will be Rp. In the volume case, it comes out like this. We have already seen that. Okay, and this is dV by V. Now Rp is equal to Rq plus 0.5 Fs n hat. Now again you have this RQ, you have RP, okay, and this vector is this half 0.5 FSN, just because this entire thing is dF is equal to Fs dA. Okay. This is already shown to be dV. Okay, so this part of half Fsn has been done just like the previous case. Please do this again. Okay, please draw the vectors very carefully. I'll put this in red. RQ dF by F, okay, plus something in the direction of n hat, and this is RR plus something in the direction of n. Okay, so this point R, which is where this resultant force acts, RR is equal to RC minus this. Okay, this implies that FR acts through, sorry, this is RC star, centroid, not the center of mass, through C star. So this will be FR equal to V, and the centroid would be somewhere over here, C star. Okay, remember this is the centroid of the volume which you have generated. Okay, so be very clear about where each of these points are acting. Now if Fs is uniform, then clearly Fr is equal to Fsan, just like over here. For a uniform. Okay, and acts at the centroid of the plane area. So I think we should put it as okay. So for uniform area it will look something like this. So if this is the area, the uniform loading will actually look like this. Okay, so the resultant Fr will be equal to Fsan, and then this is clearly Fs. It's uniform, so it's not varying with where you are on this area. This is plane area A, and this is also the centroid somewhere over here, C star. So it passes through the centroid. Okay, so let me not draw the centroid, let me draw it somewhere in the middle. If I draw over like that, it seems as if it's the centroid of this surface, which it's not. Okay, and this is where if I write, so say the centroid is C star somewhere over here. Okay. This is a plane area. Okay. This is also a plane area. And in the case which is similar to the line, the results will still hold if this area is not actually plane but curved. Okay, so it's not lying on one plane. So if you have this as your curved area, okay, so clearly the lines would be somewhere like this, and you would have a, okay, pardon my diagram, but I hope you get the idea. And in a very similar way, you would have to take the projections. Okay. Actually, in this particular case, you know that even though, and this is the point which you should note, that even though this C star is actually the volume of this solid which is generated, the C star of the area, okay, of this plane curve will also lie just below it, because it will be the same line. Okay, so that is why it is said that this FR acts on the centroid of the plane area, because both of them will be connected by a line. This red C star and the blue C star will be connected by a line which is parallel to N. Okay, hence this, it will not matter if you say that it lies on the centroid of the plane area. Okay, just like it will not matter if you say it lies on the centroid of this top area, okay, or any other cut area. So theoretically it should be the center of the body, but for a uniform case, okay, it lies on the centroid of the area, just like in this uniform case. Ideally it should have been the centroid of the area which is shown to you in green, okay, but it would not be wrong to say that it also passes through the centroid of the line, I'm sorry, over here, this one, C star, okay, because they are lying along the same particular straight line parallel to N. So that's why it can be said that it acts through the centroid of the line itself. Okay. Now if so these are some special cases. So just like we took a uniform loading and now a non-uniform loading, so let's take a non-uniform loading for this area. So if fs x comma y is equal to fs of x, okay, only varying with x, just so that we can visualize better, acts on a rectangular area in the xy plane which is uniform along the width. Then the surface force distribution can be replaced. I will show how. Okay, can be replaced by an equivalent line force distribution. FL is equal to FSB on the center line of the rectangle. Okay, so let's just first see how we can show this. So let me draw the y-axis. This is the x-axis, and clearly this is the z-axis. Okay, now this is such that the force density varies with x. Okay, so the area is made up of this B, and this is B in total. Okay, and the force is acting, say, like this over here, and it's acting like this over here. And let me choose a color. So it varies, sorry, something like this. Okay, so it goes up and it so what I do is, just like always, I take a small stripe. Okay, take this P point. Okay, and this blue one actually shows this force distribution, Fsx. Okay, and if you want to take a small force on this small area, so that would be force on B dx. Okay, because this distance is dx, this will be equal to df is equal to fsb dx, and this will be equal to fl dx. This quantity fsb is written as fl, and I'll show what that is now. Y x, okay, this is z. This is, say, a b de. So this fsb dx can be written like fl dx. Okay, and this P is again lying where it was. This length is now dx. Okay, actually I should show it with a different color, otherwise it gets confusing. Okay, this length is dx and dx. Okay, yes, it will be the same. I mean, along this entire length it will always be dx, but just using this different color helps us signify it slightly better. And clearly this is at this point x, beyond which this is dx. So the force on this, force on dx is equal to FL dx, where FL is the force density in per unit length. Okay, now this is clear that if Fsxy is equal to Fsx acts on a rectangular area in the xy plane which is uniform along the width b, okay, then the surface force distribution can be replaced by an equivalent line force. This one is that equivalent line force distribution, FL equal to FSB. So this will give us FL FSB on the center line of the rectangle. So the center line is important in the sense this is b by 2, this is b by 2. So these will be quite useful in some of the situations which you may face. Okay, and the good part about this is, I mean, it's not exactly necessary that if this Fs is symmetric. Okay, so it goes up and goes down symmetrically. There is no such requirement. So that's always a good thing. Okay, to have as less restrictions as possible. So the last definition which we can sort of get over now is for pressure, load on a plane, area, the point R where the resultant force acts is called the center of pressure. In general, the simplest resultant of a pressure distribution on a curved surface may be a wrench. We have already seen this. Okay, center of pressure may not exist. Revise from earlier. Okay, so now we can take up the next topic, next section, which is the Newton's third law of motion. Now if you remember, the Euler's axioms have already told us about the Newton's first and the second laws. Okay, please go back and check which Euler's axiom is a direct statement of which Newton's law? Okay, so now is a good time to pause if you don't recall and go back and check that. Okay, so let's state the Newton's third law of motion directly. Loads, when by loads we mean forces and moments of interaction between two bodies or their parts have equal magnitudes. Okay, and opposite directions. This is the Newton's third law, that the loads of interaction between two bodies or their parts have equal magnitudes and opposite directions. Okay, we had clearly done that also anyways, but let's put it out more explicitly over here. Okay, let me have a few diagrams, simple ones. You have body 1, body 2, contact at point P, contact at point Q. Okay, so you have and you have B2, B1. Okay, so let body B1 interact with body B2 at a contact point. Okay, that contact point is P and Q, so P is a part of B1, Q is a part of B2, so they are in contact like this, or over a contact surface like over here. Okay, so there is a surface which separates B1 and B2 in this case, and so hence these are in contact over a surface, or at a distance which is over here. B1 and B2 are separated by a distance. Now let the action of body B1 on body B2 have force sum F21. Okay, this is the action of body 1 on body 2. So the force is acting on body 2 by body 1, and this is all the forces, right? It's the summation of all the forces, and moment MO21 about O. Okay, and O is clearly a fixed point in inertial frame. Remember, we had earlier said that the Euler's axioms were valid only in the inertial frames. Okay, hence this O now has to be in the inertial frame. And the action of B2 on B1 have force sum F12 and moment sum MO12 about O. So let me just draw this as this is O, F1, 2, that should be slightly offset. F12, MO12, and over here O, F21, MO21. Okay. Okay, so I think these two forces are clear. Now then we are stating it over here, we will show its proof eventually. F12 is equal to minus of F21 and MO12 is equal to minus of MO21. This is 2.20. This implies of MA12 is equal to minus of MA21 for all points A. Okay, we'll show this now. Let's prove this. Now let the external loads, external load due to surroundings of B1 and B2 be a force sum F1 star and moment sum MO1 star about O on B1. Okay, so on B1 let this MO star 1 be the moment sum due to the surroundings and F1 star be the force due to the surrounding. So star represents the force due to surrounding on B1. Okay, and F12 is clearly the force on 1 due to 2, and MO12 is the moment sum on 1 due to 2. So that's already shown. Now very similarly we would have a sum force F2 star and moment sum MO star 2 about O on B2. Okay, so over here, so this is B2. Okay, let this be MO2 star now. Let me do something different. This is B2, this is B1. Okay, so I think this diagram and this diagram is clear. Okay, it shows the forces by the surroundings on B1 and B2 and also due to the other body. For example, F2 star is the force on body 2 due to surroundings. MO2 is the moment sum on 2 due to surroundings. F21 is the force sum on 2 due to 1, and MO21 is the moment sum on 2 due to body 1, this one. Okay, so that part is all clear. Now we have to apply Euler's axiom axioms to B1 alone, and this is the reason we had taken that O is a fixed point in an inertial frame. Okay, if we were not saying that, then Euler's axioms couldn't have been applied. So apply Euler's axioms to B1 alone, to B2 alone, and to B1 union B2. So B1 union B2 is already shown to you over here. Okay, so let's see. Okay, so the change in momentum in the I frame of 1 is equal to the total force, which is the force due to body 2 and the force due to the surroundings. Similarly, the change in moment of momentum, rate change in moment of momentum of body 1 about point O clearly is MO12, the moment plus the moment due to the surroundings. Okay. So this is for Euler axiom which is applied on B1 alone. Now we want to write Euler axiom on B2 alone, so that would just be to 1 plus M2 star. Okay, this is B. Now we want to lastly apply the Euler's axiom on B1 union B2. Okay, meaning you see B1 union B2, something like this. B1 union B2, both of them together. Now what is the, let's see, P of P1 plus P2 I. So what is the external forces? It is only the external forces because of the environment. So the forces due to the surroundings is F1 star plus F2 star. Okay, so individual forces now will not be counted over here, because you are seeing B1 and B2 as one system over which you are applying the Euler's axiom. So this is C, and the second Euler's axiom would be H dot B1 union B2 in the I frame. This will just have the moments due to the surroundings, because the moments due to the other body will not be contributing over here. This is D. Okay. So over here we can just show that this will be MO star 1 plus MO star 2. Similarly, it will be some F1 star plus F2 star, only due to the surroundings. Okay. Now and this quantity will also be equal to this quantity, can also be written as P dot of B1 plus P dot of, let me just write P dot of 1 in the I frame plus P dot of 2 in the I frame. Similarly, this can also be written as H dot 1 plus H dot O2. Okay. Now put A and B in C and D. Okay, so let's do that. F1, I'm looking at C now. Okay, F1 star plus F2 star is equal to P dot 1 is what? F12 plus F1 star plus P dot 2 is F21 plus F2 star. Okay. Similarly, looking at D now. Okay, we have MO star plus MO2 star is equal to HO1 dot is MO12 plus M star O1, sorry, star O1 plus F21. We want to write now HO2, that would be MO21 plus MO2 star. Okay, now lots of cancellations will happen, and this will imply that F12 is equal to minus of F21. Okay, this will imply that MO12 is equal to minus of MO21. 2 1. Okay, now some comments about this. So this proof is complete. Some comments is that Newton's third law is not an axiom because it is, as you see, derived from Euler's axioms. Okay, so B1 and B2, as you know, can be finite or infinite parts of the same body. We have shown that already, that it can at least be finite parts. Finite or infinitesimal. Of the same body. So you can clearly see that there is an action and reaction, okay, by looking at this and this for loads, whether it be force or moment. And here is one thing which you should note. The term action and reaction do not imply cause and effect. Rather, a mutual interaction. Is implied. Okay, so we should not see the Newton's third law as a cause and effect theory, that if there is a force acting on this, then as its effect we will have a reverse force. No, it's just a mutual interaction. They have to happen like that. Okay, it's not a cause and effect. It also implies a very important understanding of forces. A single isolated force in nature cannot exist. Okay, so we have discussed the Newton's third law over here. Now, before we begin discussing our next topic, which is kinetic energy, power and work, there is one small sort of exercise for you to think about. I have proven for you this and this, okay, 2.20, but not this. So for some reason, because of 2.20, this is valid for any point A. Okay. Now you have to come up with a reason based on what we have learned in this course, that why is this true. Okay. So if this point A was over here and over here, okay, this would still be true. So please come up with the proof of this one. You based on equation 2.20. Okay. Now so the first statement about energy is that it's a primitive, okay? Not a defined entity, it's a primitive, and this can be transformed into various forms. Okay. So in classical mechanics, mass and energy are not inconvertible. So you cannot convert the mass into energy and energy into mass. Okay. E equal to mc square is not valid in the classical mechanics. So we follow the classical mechanics for our problems, and most of the engineering problems around you are solved using this. So that's why we are working in this particular area. But yes, if ever relativistic mechanics or some sort of other course in physics in which you do, you already are aware of the interconvertibility between mass and energy. But that's not what we'll be discussing in this particular course. Okay. Now the kinetic energy with respect to frame F is defined as half into velocity of P df whole square. Okay. So what this means is that if you have, say, a frame F, this is point O, this is a small mass dm, okay, and this is the vector P or P. This has a velocity of P in the F frame. So the kinetic energy is defined like this. So if you write this velocity of P in the F frame in the Cartesian system, one would get this as x dot squared plus y dot squared plus z dot squared into dm. Okay, so this is 2.21. In the cylindrical coordinate, we can write this as r dot square plus r square phi dot square plus z dot square dm. Okay. Okay. So you should already be knowing that how is the velocity in the cylindrical coordinate written like this. Okay, so please go back and check if you do not recall this. So the position of this point P can be in the Cartesian system. It can be also in the cylindrical system. It can also be in a spherical system, but we are not going there. Okay, where x, y, z and r, phi, z are Cartesian and cylindrical coordinates of P in F frame. Okay, so a body like this one, which has kinetic energy, has the capacity to do work. You already know what work is. Okay, there is some displacement of the point of application of force, and one example of this is a pile driver. So please look up what a pile driver is and how does it work, and how this having a kinetic energy means that it has the capacity to do work. Okay, so it's used normally for drilling and other such purposes. Now the power is what Fw dot time with respect to frame F of a force F acting on a material point with velocity v in the F frame at time t. Okay, and coordinates x, y, z and or r, phi, z is defined so the power in the F frame at time t is defined. It's a defined entity. Okay, F into t dot this is 2.23. Now if you take a dot product of two vectors in the Cartesian, you would get fx vx plus fy vy plus fz vz, or fx into x dot plus fy into y dot plus fz into z dot. Similarly, in the cylindrical system, this would be fr vr plus phi v phi plus fz vz. Fr r dot plus f phi r phi dot plus f phi r phi dot plus fz and z dot. So this is 2.24. okay, and this particular can be visualized. So if this is the body and this is your F frame, this is point O, let's consider this, okay, somewhere over here, and you can say then that if this point has a velocity of it has a velocity in f at time t, it has a force at time t, okay, and this is r. So r can be written in x, y, z or r phi z. Okay, in the path coordinate, this would have ft vt, okay, or ft s dot. So if this is, say, the path s, now the work done, which is W with respect to f frame f by force from time t1 to t2 is defined. So the work is now defined after power, okay. This is something which you should note. We defined the energy, kinetic energy, we defined the power, and now we are defining the work. So I hope this sequence is somewhat clear. Okay, so this is 2.25. Okay, so this W dot is coming from over here where we had defined the power, which is 2.23. Okay, now this can be written again from t1 to t2, and this integral has been written as fx x dot plus fy y dot plus fz z dot dt. It has been written as f r r dot plus f phi r phi dot plus f z dot dt. t1 t2 ft s dot dt. Okay, this is 2.60, 2.26, sorry. So this is in the path coordinates. So we consider two cases. After having learned about this kinetic energy, power and work, let's consider these two cases. First is that f of t acts on different material points at different instants. So let me draw a nice diagram which goes with it. Point of application P in F. Trajectory of material point 1. This is trajectory of material point 2. So two different material points. Okay. And locus is the path of application of path of a point of application P in F. If F is the frame, if this circle means a frame. Okay. Now the locus of its point of application in F differs from the trajectories of the material points on which F acts at different instants. The locus of its point of application in F differs. So I think it is clear that when I say in F, it is the frame F. From the trajectories on which F acts different instants. So you can see this dashed line is the locus of point of application of force, and trajectories of the material points 1 and 2 are already shown with a solid line. So as you see that they are two separate things, I mean there is no commonality between them. Okay. Now let me just put up equation 2.25. In equation 2.25, I also want the diagram to be here, that's why I am doing this. So the work done is equal to T1 to T2 W dot F dt is equal to T1 to T2 F T dot dt. Okay. Now in this particular term, this quantity V F T dt is not equal to dr of the same material point. For all t, right? Because the because the force of application and the point have to be same at that instant. Okay, and since as the time changes, the force will be acting on some other point, so we cannot say that this particular quantity v dt is equal to dr. Okay, for all time, or even drp. Not neither of them is true, so this is something which isn't read, and you should verify this. Okay, so if I draw what, so for point 1 at this given time, you have, say, f acting at time t1. Okay, the r1 dot is equal to v1 into t1. Okay, this quantity is also dr1 t1 equal to v1 t1 dt. Okay, and this over here is drp t1. Similarly, over here, say you have this as f at t2. Okay, ft acts on different material points at different instants. So at material point 2 it acts at time t2, at material point 1 it acts at time t1. So over here you will have a drp t2 r2 dot is equal to v2 t2 and tr2 t2 is equal to v2 t2 d2 dt. Okay, so this is a case of where this force acts on different material points at different instants. One can also see a physical example of this, that is, say you have rolling without slipping. Okay, so this point P over here, this has a normal force which acts, this has a friction force which acts. Okay, and this is the center. Now at the next instant, I'll show this with a dotted line. Okay, so this is in the next instant. The force acts on this point 2. Okay, this point is 1, this point is 2, and P is the general point. Okay, P is the point of application of this force, both F and N. I mean, you can take the resultant. So at this instant 2, the force acts at material point 2, which is clearly different than of what was 1. Okay, so let me show a 1 dash over here. Okay, this point has actually moved up over here. So the trajectory of this point is something like this. So this is the path of material point. Of application. So material point 1. So you can see that the material path which is in blue is different from the locus of point of application. So the locus of point of application is along this direction. So this is locus of point of application of force. Okay, so the green and blue paths are different, and that is the meaning of this situation, that f of t acts on different material points at different instants. Okay, now you can try to verify this in red using this rolling without slipping example. Okay, so the contact point, this contact point over here, this 1 or P, the contact point has zero velocity in rolling without slipping, and you know that it's also caused an instantaneous center of rotation. Therefore, the power of friction force F acting at this material point is 0 for all times. Okay, because you see the power is where did it go? Power is equal to ft dot v. So since this v will always be 0, hence the power will always be 0. Wherever that force is acting at that point, the velocity is 0. And the work done, this implies the work done, okay, by F is also 0. Okay, and it does not equal to F dot Et ds, okay, where ds is the arc length traced by locus of point of application on fixed surface, basically the green line which I had drawn. Surface. Now one can take the second case now. F of t f of t acts on the same material point at all times t. So f of t acts on the same material point at all times t. Okay, this can be an example of force f of t acting on a center of wheel. So look at this situation. this is a center O, and this force T1 is acting. Maybe you're trying to pull or push this wheel, and the velocity of this is at time T1 is this. Now okay, so the force Ft acts on the same material point at all times t. So F of t acts at the center of the wheel. Okay. Now if you look at 2.25 again, this in equation 2.25, V in the F frame dt is equal to drf, where drf is the differential displacement of this material point. Material point with path C in F frame. Okay, when I write in F, you should understand it is only the frame F. So sorry. So in this particular case, you will have, say, a trajectory like this. Okay. C is the trajectory of material point. Okay. It is also the locus of point of application of force. Here they are coinciding, and at this case, in this case, say at time t1 over here, you will have F acting at t1. Okay, and one would have in this case TRP. So point of application, okay, is P. DRP of T1 is equal to V T1 TT, and then R of P dot of T1 is equal to V of T1. Now at T2, similarly, if you look at this diagram, we have F of T2 DRP T2 VT2 DT to v t2. Okay, so this is the case where ft acts on the same material point at all times t. Okay, when the example is that f of t acts on the center of the wheel in this particular way. Okay, so drp, sorry, in this case is the differential displacement of this material point p. Okay, this is the material point p or o, whatever. Okay, fine. So 2.25, now we can write w is equal to r t2 along a path is c, okay, t1, and this is f dot dr. So along c we have x comma y comma z at t1, so I'm just writing the coordinates, and then we have x comma y comma z at t2. In this case it will become fx dx plus fy dy plus fz dz. Similarly, in the cylindrical coordinate system, the same path has to be followed: r phi z at t1, r phi z at t2. Okay, so fr dr plus f phi r d phi plus fz. Okay, so this is all equation 2.28. Now again we can write this in the cylindrical system as well, just that we have not, sorry, spherical system as well, just that we are not doing that in this course, but it's possible to do that in any coordinate system. Now the line integral which you see over here, okay, has to be calculated along the path C, okay, and not along just any curve which lies as a part of the curve may be traversed more than once. So I'll show what it means. This line integral, all these three are line integrals. These line integral have to be taken along total path C and not merely along geometric curve along which it lies as a part of the curve may be traversed more than once. Let's see that with the diagram. So this is at t1, this is at t2. Okay, so the curve is this solid line, but the path may be like this path, okay, and then The black is the curve. So you must do this line integral calculation over the green path. Okay. Because you can see like it goes up and then it comes back and then goes ahead. So all that must be done, captured in this. So it's just like and in a general force that must be true. Like if you say push a block for some distance, push it back and push it back again, so you should not just take the displacement between those points. You have to do that integration to calculate the work due to friction on this block over the whole path which it has followed. Okay, now the black and the blue over here will be identical only if the material point moves in one direction on its trajectory. Okay, the curve and the path will yield identical W. So we have dropped this F frame over here, okay, just so that I think it was obvious. So everything is in the F frame. So the curve and the path will yield identical W only if the material point moves in one direction. Okay, in one direction on its trajectory. Now if the force is time independent, I'm sorry, if the force is time dependent, meaning it will change with the time, then the work in equation 2.27 is not strictly a line integral. Okay, so this is a statement, perhaps you can, it's obviously clear coming from here to here, but you should verify this. Okay, now if the force acts on a specific material point at all times and depends only on its position vector r, if in this case, okay, let me just say in this case force acts on a specific material point at all times and depends only on its position vector, or that is it is of form FR, then this 2.27 equation 2.27, which is what W is equal to the path going from R to T1, R to T2, F T dot dr is used to find work. Okay, provided either path C is known or force is conservative. So you already know what a conservative force is. Okay, what it is that the work is independent of path between two positions RT1 and RT2. So if the material point is at RT1 and it is at time T1 and it is at R of T2 at time T2, then if the work done is independent of the path taken between these 2 points, then you call that force as conservative. So you may have to do some other manipulations for converting the integrals over here in 2.28 in this one. Okay, so you can convert 2.28 into parametric form. We have already done this before, but we'll do it once again. All it requires you to do is say do something like let me just write that over here, and let me write one of them over here. So in parametric form, so W is equal to C of R of tau 1 R of tau 2 F dot dr. This would be equal to tau 1 to tau 2 fx of tau dx by d tau plus fy of z dy by d tau plus fz of z fz of tau, sorry, okay, this is tau, fz of tau is dz by d tau into d tau. Okay, so this is the parametric form, and I mean you can use now any parameter. So just substitute tau equal to x in that, so fx will now become f of x comma y comma z is equal to f of x comma y comma x of y x comma z of x. So hence this is only a function of x. So w will then be x1 to x2. You want to write fx as a function of x clearly. Dx by dx will be 1, fy of x. Dy by dx will be dy by dx plus fz of x will be equal to dz by dx into dx. So this is how you can convert it to any parameter. Time, I think, is obviously you will get back what you had started off with. So that's where we end our discussion on kinetic energy, power and work.